right. Hi, everyone. As Eric said, these couple of short presentations aim to give you an overview of what optimization is about. And as the sub-theme says, it's about formulations, algorithms, and the areas of applications that we might encounter using optimization. So what is optimization? This is due to a well-known mathematician, Roger Fletcher from Dundee University, retired now, I think, who said that optimization is the science of finding the best solution. And as we'll see, the best solution to what problem is what corresponds to the formulation, and best solution with what criterion corresponds to what we will call the objective function. But this is a very short and nice definition of the topic. So the main areas of this presentation will focus in three interconnected subdomains as I show them here. We'll start, or we will highlight applications as we go through in our discussion, then find what formulations capture the physics and the modeling of the application we're interested in, and then once we have the formulation, we need to find what suitable algorithm we want to use to solve it, and at every step of the way, there's two-way feedbacks. Basically, if you find a formulation, let's say, that is applicable to something else you hadn't thought before, you generate opportunities for the creation of new applications, which could be new materials, could be new anything. Similarly, if you find an application that's hard, you may be inspired by a formulation that already exists, which will allow you to go to the solution direction, and vice versa. Sometimes you have formulations that you can't solve with anything, so you're forced to invent algorithms, like some of my students are kind of doing. So this is the chain of work in the area of optimization. So here's an overview now of the whole presentation, which covers both days, today and Friday. So the first thing we will go through is what is the statement mathematically, as well as verbally, of what optimization is. We're going to talk about convexity and non-linearity, two very important concepts in optimization theory. We're going to talk about argument types, variable types I wrote here, that an optimization problem might involve. I'm then going to go into an informal discussion about the curse of dimensionality and how it affects the decision-making processes that optimization might be engaged in. Then we are going to talk about formulations, and we're going to see about generalized optimization problems, classes of problems. Then, most likely in the next lecture, we are going to continue looking at things such as algorithms, important algorithms that define the field in the last and this century, and then have some conclusions from all this work. So let's look at the optimization problem statement. An optimization problem has three ingredients. I have four there, but two are the same. The first ingredient is, what is your aim? Are you trying to minimize something or maximize something? By manipulating what degrees of freedom, what variables? So you either have a minimize with respect to x or a maximize with respect to x of some criterion, function f of x, which could be an economic criterion, for example. Minimize cost or maximize profit. The next most important part in engineering problems, particularly chemical engineering problems, is the equality constraints part. The equality constraints, there's nothing you can do about them. You have to always satisfy them with your choices of your variables x. And where they come from is from the model itself of the process you're trying to control or to regulate in such a way so that you increase profitability. The third ingredient is inequality constraints, which could be less or equal or greater or equal to right-hand side, to 0, for example, in this case. A class of them is bounds. It's clear that they're a specialized form of inequality constraints. And where they come from is from either quality restrictions on your product, operability restrictions that you are not allowed to exceed a certain operating envelope, or simply physical limits on the variables of your system. So this is what we call the general mathematical programming problem. If all the variables x are continuous, then we simply call it the nonlinear programming problem. And then I'm going to repeat what I said verbally about the various aspects of the model. So first of all, the objective is our aim, the target, like a minimum cost or maximum profit. The quality constraints can be, they're the modeling equations of your process, and they can be anything of these items. These are linear algebraic equations, if you have a linear model, nonlinear algebraic equations, ordinary differential equations, differential algebraic equations, partial differential equations, and I could have added integral differential equations as well here, but I stopped at that point because it's very clear what's going on. And then, as I said, inequality constraints could be either operating limitations or quality control constraints. The bounds, they're implied by inequality constraints, and they usually arise naturally from the problem definition itself. Since these are informal, the presentations, if you have any questions or you want to expand a bit further on something, we have plenty of time with the 2 lectures to do that, and I would like you to interrupt anytime you want. So the next item is to talk about convexity and non-linearity. Non-linearity is pretty well established what it is among this audience, and whenever it arises, it complicates definitely the solution procedure, but in itself it is not the most important complicating factor of your model or your optimization task. The complicating factor is non-convexity, either of the objective function and or of the constraint set. This causes serious complications and has implications in practical applications of optimization, as we will see immediately now. So a convex function looks like this. It looks like a ball, and it has clearly a unique local minimum, which is also the global minimum, which you can identify easily at the bottom of this valley. And the case is the same whether it's one-dimensional or two-dimensional or n-dimensional. Non-convex functions, on the other hand, they look like this in one-dimensional problems, or like that in two-dimensional problems. And effectively, what characterizes them is that they are not convex, like a ball everywhere, but they have local regions where they might be convex, and they may contain minima in those regions, which are only local. For example, if I perturb left or right from the point I'm showing here with my finger, there's no better solution locally. But if I go further away, the global solution might be this one. So locally, you don't find a good point with a small perturbation, but with a big perturbation, if you're considering the whole domain of your variable, it's not the global solution to guaranteed to be in one of those local minima. And there is an easy definition, a geometrical one. A convex function is always overestimated by its chord, as is shown there. The chord is above the function, and so we have the convex situation. For minimization, if you have a function like this, it is guaranteed that what you will find as a local minimum will also be the global minimum. A concave function is the mirror image of the previous situation, and it's always underestimated by its chord. For maximization, now, this is a guarantee that it will have a unique global maximum. Now, for all optimization problems, we have one further requirement. If you're to guarantee the global solution of your problem, it's not enough for the function to be convex for minimization or concave for maximization, but you need a special property also on the set of values where you draw the values of the variables. So the constraints need to define what we call a convex set. A convex set contains all the points of the line connecting two of its points. So if you have 2 points belonging to a convex set, when you connect them with a straight line, every point on the line also lies within the set. Otherwise, you have a non-convex set. And that's the definition of convex set. So if you have a convex function, if you have a convex set of variable values, then you're guaranteed that your solver, whatever your problem is going to give you a unique solution. And it will be the global. Now, interestingly, some years back when I was teaching parts of this to a class, they asked me, and what happens when you have a concave set? And I said, there's no such thing, because the definition of convexity is only whether the points are contained within the set. If they're outside the set, there's no concept that this can apply to. So just as a clarification for people who are new to this. Now, just a demonstration here. Even if the objective is convex for minimization, if the constraints are non-convex, then you have multiple minima. So what do we have here? This is a contour plot, and my objective function is linear, and its contours are straight parallel lines in a two-variable space. And the direction of decreasing value of the objective function contours is this way. Because it's linear, if you didn't have a constraint, this would have gone down to minus infinity. But here we have a constraint, and obviously this descent is going to be stopped at some point where the contour is about to leave the feasible space. The feasible space is above this shaded area. So we notice, though, that we have 3 candidate points where if you push it beyond this, the constraint becomes infeasible, and yet you could reduce the objective. Therefore, this locally here is a local minimum, because anywhere around it you have either infeasible points or you have worse value objective points. The same with this, and the same with this. So all these 3 points as drawn here, they're candidates and they're valid local minima. And a solver which only looks at local properties of the function, like the gradient, will stop at either one of these 3. And you won't know whether you've actually hit the global one, which is this one here, which has lower objective. To actually be able to identify this, you need specialist algorithms, which I will discuss later in the second part of the course, of the, lectures. So what can we solve? Many things. Even non-differentiable problems where your functions have discontinuities, either in the gradient or the value. The general nonlinear programming problem, NLP, will have no certificate of global optimality if it's not a special class of problem which is called Convex Programming problems. We have special algorithms for general problems. If you want a certificate of global optimality, this will come at a high computational cost, long computational times, and the size of problems that you can handle is usually very restrictive for realistic, let's say, industrial scale applications. I don't think anyone can claim that that there is a global solver that can handle huge scale problems currently. There are people who are making serious progress, but we're not there yet in the huge scale. And then we have special problem formulations, the convex programming problem, which is the only one that has a certificate of global optimality, even though you're using a non-specialist algorithm. So what is a convex programming problem? First of all, you have an objective function which is, for minimization, convex, and it's subject to affine equalities, what engineers call linear. In pure mathematical terms, strict terms, is called affine, meaning that you have a linear term equal to a right-hand side, and then your inequalities are, and they have to be also convex functions, strictly. And x are continuous variables. If your problem formulation falls in this category, in this class of problem, then you're guaranteed that you only have one solution, which is the global one. And it can be solved in terms of complexity in polynomial time, and there's a 1995 proof for that. So having seen this thing about what is an optimization problem mathematically, the formulation, and what types of complications we might have, we embark now on exploring one other dimension of optimization applications, which has to do with what type of variables, what type of arguments are your degrees of freedom in the problem you're trying to optimize. So the typical case is where your variables belong to the real set of continuous numbers. And if you have n variables, then they belong in Rn. In many applications of engineering interest, particularly in chemical engineering, these variables happen to be integer, not just continuous, integer. A special case of them, even, is when they are binary variables. They're only allowed to take values 0 or 1. And this is used to encapsulate Boolean operations, the absence or presence of a unit in a flow sheet, on-off operations, on-off control. You're allowed only two values, a boiler on, boiler off, no intermediate gradations. And then another case is where the arguments themselves are functions, in particular either of space or time or both. And this we'll see later. So here is the case where you have a function in two variables, x and y. Your x is nicely continuous, can take any fractional value, but y is only allowed to take integer values. So optimization of this function is equivalent to the following. Choose the level of variable y, which gives you a continuous function in x, and then minimize that with respect to x. So each time you fix what I'm trying to say, the value of variable y, you get a continuous function, which then you have to optimize. And yet, somehow, you have to come up a solution for both x and y simultaneously for such problems. We'll see some examples of how these are handled. The next item I want to cover now, and I will speak very much in loose terms of what the curse of dimensionality is by examples. How the dimension of your problem might affect the difficulty, the effort it takes to solve the underlying problem. So let's look at this. Let's say we assign 10 intervals for each variable. And we have 100 variables. We are allowed to evaluate once the function in each compartment of the discretization. That means in order to pick the minimum, if we were doing brute force enumeration of all the points, would require 10 to the 100 function evaluations. This is a bad algorithm because it runs in exponential time, as shown in the example. For example, to find with the same precision, let's say, my single variable problem solution, I would need 5 evaluations. If I had 2 dimensions and the same discretization step in every direction, I would need 25. And similarly, if you go to 3 dimensions, is n to the 3, in which case is 5 to the third, which becomes 125, and this grows very fast. And this is a bad algorithm if you try to optimize a multidimensional problem using this approach. Now, this is, again, what I said. I will talk in loose terms about how a single function evaluation characterizes information around the point you evaluate for a given function f of x. So let's say we have a function f of x in one dimension, and the interval we're trying to find the minimum, let's say, is big delta. Okay? And then I'm going to pick a single evaluation at point x naught, and to see how far I can go around it, I define an error, and I say I don't want the function to go beyond epsilon error for the middle value that I picked for this point x naught. So if this value is f naught here, I don't want the error to be f minus f naught absolute value greater than epsilon. So let's say the corresponding interval to this error epsilon that I've set is little delta. So taking these two values, basically I'm saying in a big delta interval with an epsilon error, I have a little delta interval that I can tolerate and sort of say that my value of x naught is kind of typical, gives me typical values for f that don't deviate more than epsilon. Take the ratio. That's what I'm going to do. But before I do it, I'm showing the same picture of the same error epsilon in examples as the dimensions grow. So in 2 dimensions, the error epsilon, let's say, is confined within a square, a square domain of little side delta, while the big domain has side delta capital. And the same here, it's a cube within a bigger cube in the domain. Is this so far clear? Okay, so now I'm going to generalize it to n dimensions and take the ratio. The fraction of the hypervolume characterized by a single function evaluation is given by this. And this, by the construction, is always less or equal to 1. Strictly speaking, it will be less than 1 unless your function is totally flat, if it's linear. So no matter what you do, as you go to larger and larger and larger dimensionalities of your optimization problem, this fraction will decay exponentially with the number of dimensions. Or conversely, we need an exponential number of evaluations to characterize a percentage of the search volume. And this I will show later in another picture. But before I do so, I want to look at a second implication. Yes?
Well, thank you.